All right, welcome to another deep dive. This time, we're going on an adventure into the world of chemistry simulations, and specifically, we're looking at this open source educational resource that was sent to us from Singapore.
Cool. I'm excited to dig into this with you.
Me too. So, just to give everyone a quick overview, this resource is basically a web page with a JavaScript HTML5 applet that simulates concentration changes.
Yeah, so it's like having a mini program running right there on the web page, which creates this interactive environment, where you can experiment with different scenarios.
Right. And for anyone who might not be super familiar with the technical terms, a JavaScript HTML5 applet is, well, it's basically just a fancy way of saying it's an interactive element within the web page itself. So, not something to be intimidated by.
Exactly. It's designed to be user-friendly and fun.
Okay, cool. So this simulation lets you play around with different variables and see the impact on concentration all in real time. But I gotta admit, when I first saw this, I kind of thought, is this just like a high school chemistry thing? Like, are there any real world implications to understanding concentration changes?
Oh, absolutely. This concept is way more practical than you might think.
Yeah.
You see it playing out in all sorts of fields, from environmental science to medicine.
Interesting. Could you give us some specific examples?
Well, think about pollution control, for instance.
Yeah.
How quickly does a pollutant disperse in, say, a lake? Or in the medical field, calculating drug dosage. That's a big one.
Oh, yeah, drug dosage.
Right.
That brings back some memories of trying to figure out those tricky problems in high school. How does concentration come into play there?
Well, imagine you're a doctor trying to determine the right dose of medication for a patient. The concentration of a drug in the bloodstream.
Mm.
That's critical for it to be effective, but also safe.
Mm.
And this simulation, well, it helps visualize how factors like the rate of absorption and the body's elimination processes, how those affect that concentration over time.
So it's not just about like getting the right amount of medicine into the body, but also understanding how it behaves once it's there.
Exactly. It's about finding that sweet spot
Right.
where the concentration is high enough to be effective,
Yeah.
but not so high that it becomes toxic.
Wow. Okay. So this is starting to sound a lot more relevant to everyday life than I initially realized.
Right. And that's just one example. There are so many others, like in industrial processes, optimizing chemical reactions.
So big picture, this simulation is helping people learn about the science behind a lot of important stuff. But one thing that really struck me about this resource is that it's part of Open Educational Resources, open source physics at Singapore, which means it's free and accessible to anyone with an internet connection. Imagine that. Having access to this kind of learning tool no matter who you are or where you live.
It's incredible, isn't it? This type of open access, it really democratizes education. It levels the playing field for learners all over the world.
It's like opening up a whole new world of possibilities. Makes you wonder how many curious minds are out there just waiting for the chance to learn.
Absolutely. And for teachers, especially those with limited resources, it's an invaluable resource.
For sure. Okay, so we've talked about the simulation itself and the whole open educational resources thing. But as I was poking around on this webpage, I noticed something else that caught my attention. At the bottom, there's this list called Other Resources. And some of the titles, well, they're pretty intriguing.
Oh yeah, it's like a treasure trove of connected learning opportunities.
It is. For instance, there's one called Projectile Motion with System of Masses and Spring.
Oh, that one is cool. It delves into the physics of motion. How objects behave under the influence of forces like gravity.
That sounds a bit more complex than what we've been talking about, but, I'm a big baseball fan, so thinking about this simulation in the context of, like, a pitcher throwing a curveball, that makes physics seem a lot cooler.
Right. It's like peeling back the layers of reality and seeing the underlying principles at work.
Absolutely. And speaking of real-world applications, there's another one on this list that caught my eye, the antibiotic resistance DICE simulation.
Ah, yes. That one's very timely.
It is. Antibiotic resistance is a major public health concern these days. What do you think they're simulating with DICE?
Well, I'm guessing it uses a simplified model to show how bacteria can develop resistance to antibiotics over time.
Interesting. It's kind of amazing how something as basic as DICE can be used to teach about such a complex issue.
It really goes to show that you don't need fancy equipment to learn about science. It's all around us.
So true. Okay, I think we've done a good job of setting the stage here. We've talked about the tank concentration simulation and the importance of open educational resources. But let's focus back on the tank concentration simulation for a moment. What makes this particular simulation stand out? What are some of its key features?
Well, one thing that I think is really effective is its visual representation.
Hmm.
You're not just looking at numbers and formulas. You actually see the substance mixing within the tank.
Yeah, visuals are definitely helpful, especially when dealing with something abstract like concentration.
Right. It helps make the concept more tangible. And another thing I like is its interactivity. You can manipulate those variables and see the results immediately.
It's like having a virtual lab right at your fingertips.
Exactly. But, it's important to remember that simulations are just that, simulations. They're simplifications of reality.
Right, they can't replace the hands-on experience of working with real chemicals in a lab.
Exactly. But they can be a great complement to real-world learning.
So who do you think would benefit most from this particular simulation? Is it just for high school chemistry students?
I think it could be beneficial for a range of learners, from high school students to even professionals in fields like chemical engineering.
So not just about introducing the concept, but also deepening understanding for those who are already familiar.
Absolutely. It can be a great tool for review or even for explaining the concept to others.
And it sounds like it's designed to be pretty user-friendly, even for those who might be new to chemistry.
Yeah, the instructions are clear, and the visuals really help make the concepts more intuitive.
Great. So we've talked a lot about the tank concentration simulation, but let's zoom out a bit and consider the bigger picture, the open source physics at Singapore website. What else can you tell us about this website and the resources they provide?
Well, open source physics at Singapore is a fantastic initiative. They're dedicated to creating and sharing high-quality interactive physics simulations and other educational resources.
And it's all open source, which is just amazing.
It is. Their mission is to make physics education more accessible and engaging for learners worldwide.
And they certainly seem to be succeeding. I'm blown away by the quality and diversity of the resources they offer.
Me too. It's a treasure trove of learning materials.
It is. Okay, well, I'm ready to dive deeper into this treasure trove. There are so many more simulations on this list that we haven't even touched on yet.
Let's do it. Which one are you thinking about?
Well, there's one called Rutherford's Atomic and Thomson's Configurable Plum Atomic Model JavaScript HTML5 Applet Simulation Model. That's quite a mouthful.
It is, isn't it? But it hints at the fascinating journey of scientific discovery that this simulation explores. It takes us back to the early 20th century, when scientists were trying to understand the structure of the atom.
Okay, I remember learning about those models back in high school, but a refresher would be great. Can you give us the SparkNotes version of Rutherford's and Thomson's models?
So imagine you're trying to figure out what an atom looks like, but you can't actually see it. That's the challenge scientists faced back then. One of the first models, proposed by J.J. Thomson, was called the plum pudding model.
Plum pudding. That's a pretty interesting name for an atomic model.
Right. Thomson had discovered the electron, a tiny negatively charged particle. So he envisioned the atom as this diffuse sphere of positive charge with these tiny electrons embedded within it, like plums scattered throughout a pudding.
Okay, I can kind of picture that. So what did Rutherford do to shake things up?
Rutherford, well, he conducted some groundbreaking experiments where he bombarded a thin gold foil with alpha particles, which are positively charged particles.
Okay.
And what he found was that most of the alpha particles passed straight through the foil. But a few were deflected, and some even bounced straight back.
Wow, so it was like those deflected particles hit something solid within the atom.
Exactly. Rutherford realized that Thomson's model couldn't explain this. He concluded that the atom must have a tiny, dense, positively charged nucleus at its center.
So like a little sun with planets orbiting around it?
In a way, yes. And that led to the development of the nuclear model of the atom, which is the basis of our understanding today.
So this simulation lets us basically relive those historical experiments that led to such a major shift in our understanding of the atom.
That's the idea. It's a great way to learn about the history of science and see how scientific knowledge evolves over time.
Amazing. Okay, before we get completely lost in the world of atoms, there's another simulation I want to ask about. The symmetry block simulation. What's that one all about?
Oh, symmetry. That's a fundamental principle in so many areas. Art, design, nature.
I've always kind of understood symmetry intuitively, but I've never really thought about it in a scientific way.
Well, this simulation lets you explore different types of symmetry, like rotational symmetry, reflectional symmetry. You can manipulate shapes and see how those transformations affect their symmetry properties.
Sounds pretty cool. I can imagine that being useful for like geometry students or even artists and designers.
Definitely. It's a great example of how science and art intersect.
Okay, we've covered a lot of simulations so far, and I gotta say, I'm feeling a bit overwhelmed by all these amazing resources. But before we get too carried away, let's take a step back and talk about the bigger picture here. What impact do you think these open educational resources are having on learning in general?
It's a huge shift, I think. Open educational resources are making learning more accessible, more engaging, and more personalized.
It's like they're breaking down barriers and empowering learners to take control of their own education.
Exactly. And it's particularly important in fields like STEM, where access to quality resources can be a major factor in determining who gets to pursue those careers.
So true. Okay, one last thought before we move on to the next part of our deep dive. We've been talking about the benefits of simulations, but are there any potential downsides or limitations that we should be aware of?
Well, it's important to remember that simulations are just that, simulations. They're not reality. They can be powerful tools for learning, but they shouldn't be seen as a replacement for hands-on experience.
Right, like the map is not the territory.
Exactly. Simulations can help us understand concepts and explore possibilities, but it's important to keep in mind their limitations.
It's about finding the right balance between the virtual world and the real world.
I couldn't agree more. Simulations are a valuable tool in the learning process, but they should be used thoughtfully and purposefully.
Excellent point. Okay, I think we've covered a lot of ground in this first part of our deep dive. We've explored the tank concentration simulation, talked about the importance of open educational resources, and even touched on some of the philosophical implications of using simulations to learn.
Phew, it's been a whirlwind, but I think we've laid a good foundation for our continued exploration.
We have. And in the next part of our deep dive, we'll continue our journey through the open source physics at Singapore website, uncovering even more fascinating simulations and delving deeper into the transformative power of open educational resources.
I can't wait. It's fascinating how these seemingly simple simulations can, spark such deep conversations about learning.
Yeah, it's true. It shows just how powerful interactive learning can be. When you can actually play with a concept, it just makes so much more sense.
Absolutely. And I love how it pushes you to think beyond just that one specific use. Like we were talking about pollution control with the tank concentration simulation. But you could use it to, model things like how a virus spreads or even how ideas spread on social media.
Whoa, that's getting pretty deep. Suddenly we're talking epidemiology and sociology,
Sure.
all starting from a chemistry simulation.
Exactly. The connections are everywhere. And it's all thanks to this open source resource from Singapore. Speaking of which, I think we should highlight the importance of open educational resources in general.
Definitely. Just the fact that this simulation is free, anyone with an internet connection can access it, that's huge. It really levels the playing field.
It really does. It gets rid of the barriers of cost and access that can be so limiting.
For sure. It's like it creates a spirit of collaboration and sharing within the educational community.
It does. And teachers can adjust the resources to fit their needs. And students can learn at their own pace, dive into topics that really grab their attention.
Right, right. It's a win-win for everyone. And I think it's especially important in fields like, STEM.
STEM.
Yeah, science, technology, engineering, and math, because access to good educational resources that can really determine who gets to pursue those careers.
You're absolutely right. So by making these resources open, we're opening up opportunities for a much wider range of students.
Exactly. It's
Yeah.
exciting to think about all the possibilities. Okay, so before we get too carried away, let's get back to that list of intriguing other resources. There were a couple more that really caught my eye.
Oh, yes, that list is full of gems. Which one are you thinking of?
Well, there's the volume of tank simulator. Sounds like it could tie in nicely with the concentration simulation.
It probably does. It might explore how the volume of a container affects the concentration of something within it. Like, a bigger tank would dilute a substance more than a smaller tank, even if you put the same amount of this substance in both.
Right, right. It's all about the relationship between volume and concentration, another key concept in chemistry.
It just makes you realize how many everyday things are governed by these basic scientific principles.
It does. And then there's the powering the alarm clock simulation. That one seems a little different from all the chemistry stuff.
It does, yeah. But it's a perfect example of how these simulations can connect ideas from different fields.
Yeah.
That one probably explores the principles of electricity and circuits. It probably makes you think about how complex even simple gadgets like an alarm clock really are.
I'm already starting to feel a little overwhelmed thinking about all the things I take for granted every day.
Uh-huh, right. It's like getting a peek behind the curtain of technology.
Okay, there's one more on this list I have to ask about. The antibiotic resistance dice simulation. That one seems especially relevant these days.
It really does. Antibiotic resistance is such a big problem, and this simulation probably shows how bacteria evolve and become resistant to antibiotics over time.
I'm guessing it uses a simplified model, but even so, it could be really powerful in helping people understand this issue.
And maybe even encourage people to be more careful about how they use antibiotics.
Exactly. It's a great example of how simulations can address real-world issues. Plus, it's interdisciplinary. We're talking about biology, medicine, and even public policy.
It's amazing how it all ties together. It makes you wonder if we can use simulations to, model solutions for other big problems too.
That is a great question. It really shows the potential of these tools. Looking at all these different simulations, I'm noticing a pattern. A lot of them involve, actually doing experiments and analyzing data.
That's a sharp observation. It definitely reflects the growing focus on what's called inquiry-based learning. That's where students ask their own questions, design experiments, and analyze data to reach their own conclusions.
Right, so they're not just passively absorbing information, but actively learning and figuring things out for themselves.
Exactly.
And these simulations offer such a safe space for students to develop those critical thinking skills.
It's like a virtual playground for scientific discovery.
I like that. A playground where curiosity and imagination can run wild.
Yeah.
But speaking of exploration, there are still so many more simulations on this list we haven't even talked about yet.
I know, right? There are so many directions we could go. What are you thinking about next?
Well, ripple tank simulation caught my eye.
Oh, that's a classic one. It's a great way to see how waves work. Remember learning about wave interference and diffraction?
Vaguely. Something about waves, like combining and canceling each other out.
Exactly. This simulation lets you create waves virtually and watch those patterns of interference and diffraction. You can change the frequency, add obstacles, even simulate different wave sources.
So it's like a virtual version of those ripple tanks we used in high school.
Exactly. Except this time you can actually explore the science behind it all.
I think I was too focused on just making cool patterns back then to really understand the physics.
It happens. But this simulation lets you manipulate the variables and see the effects in a controlled environment.
I bet it would have made those physics lessons so much more engaging.
For sure. And, it's not just physics. This simulation is also relevant to things like acoustics and optics.
Wow, I had no idea. A ripple tank could have so many applications.
It just shows how interconnected all these scientific principles are.
Absolutely. Okay, another one that jumped out at me is coupled oscillators. That one sounds a little intimidating. What exactly are coupled oscillators?
Okay. Imagine two pendulums swinging next to each other. If they're not connected, they swing on their own. But if you connect them, say with a spring, their movements affect each other. And you start to see some really interesting patterns.
So they kind of sync up?
Yeah, sort of. It's about how energy is transferred between them. This simulation lets you see those interactions.
It sounds like you could use it to model all sorts of real-world things.
You could. Think about musical instruments. Lots of instruments use coupled oscillators to make sound.
Like the strings on a guitar or the air columns in a flute.
Exactly. And this simulation can help us understand how they work.
That's really cool. Okay, one last simulation before we move on. Simple harmonic motion seems like a fitting way to end, since we've been talking about oscillators.
Oh, that's a good one. Simple harmonic motion is a specific type of motion where the force pulling something back to its starting point is proportional to how far it's moved away.
Okay, that sounds a little complicated. Can you give me an example?
Sure. Imagine a weight attached to a spring. If you pull it down and let go, it bounces up and down. The spring is always trying to pull the weight back to the middle.
So the more you pull it down, the stronger the force pulling it back.
Exactly. And that's what defines simple harmonic motion.
It's amazing how much we can learn from these simple simulations.
It really is. It shows how powerful abstract thinking can be.
Okay, I think we've covered a lot of ground in this second part of our deep dive. Open educational resources, the connections between different areas of science, and even some philosophy.
It's been quite a journey.
It has, but it's not over yet. In the next part, we'll keep exploring the open source physics at Singapore website, finding even more amazing simulations and looking at how these resources can change education. Welcome back. We've been on quite the adventure exploring open educational resources, especially those incredible simulations from open source physics at Singapore.
Yeah, it's really amazing how much we've covered, from chemistry to physics, even touching on some other fields. And you know what? There's still so much more out there to explore.
It's true, talking about all these different simulations, it makes me think about how technology is changing the way we learn. It's like these simulations are giving us a whole new way of seeing the world.
Yeah, I agree. They let us see things that would be almost impossible to see otherwise. Like really complicated concepts or things that happen too fast or too slow for us to notice.
Right. Like we can slow down time, zoom in on tiny things, or even try out situations that would be too dangerous or complicated in real life.
And it's not limited to science either. These simulations can be used for so many subjects like history, economics, even art and music.
It's true. Learning isn't just stuck in textbooks and classrooms anymore.
It's everywhere. And these simulations are giving us the keys to unlock it all.
So where do we go from here? What's next for simulations in education?
Well, I think we're just getting started, really. As technology keeps getting better, we can expect these simulations to become even more realistic and engaging.
I can imagine virtual reality and augmented reality being used more, where you can actually step inside the simulation and interact with it.
That would be incredible. And with AI, artificial intelligence getting smarter,
Right.
we might see simulations that can adapt to how each student learns best and give them personalized feedback.
It's like having your own personal virtual tutor.
Exactly. It could completely change how we educate future generations.
That's exciting. But like any new technology, there are things to be careful about. We need to make sure these simulations are used responsibly and in the right way, not as a replacement for real-world experiences, but as a way to enhance them.
Absolutely. It's all about balance, using technology to make the human experience richer, not to take away from it.
So as we wrap up this deep dive, I want to leave everyone with a challenge. Check out that open source physics at Singapore website. Discover the amazing world of simulations they have there, but don't just play around. Think about what you're learning, the possibilities and the limitations of these tools, and how you can use them to improve your own learning and the learning of others.
Yeah, and don't forget, learning should be an adventure. Have fun, ask questions, experiment, and never stop exploring the world around you.
Well said. Thanks for joining us on this deep dive. Until next time, happy exploring.